So, hello and welcome to the seminar series on artificial intelligence for predictive maintenance. I am Madhav Misra and I am hosting this seminar series. I have honors to introduce Professor Angela Mayer from Bern University of Applied Science, is Bern, Switzerland, who will present the seminar on the topic of opportunity and challenges of prognostics and health management of wind farm. Yeah. So let me introduce about the Professor Angela Mayer. Dr. Angela Mayer has been a professor of applied machine learning and research group leader at Baird University Applied Science since 2021. Before joining BFH, she was a senior lecturer in smart maintenance at Zurich University of Applied Science. Dr. Mayer research focus on increasing the reliability and performance of industrial system by means of artificial intelligence. Her research is driven by the vision of facility the energy transition by means of artificial intelligence, machine learning, and digitalization for the intelligent operation of energy system. Dr. Mayer received BSc degree from Imperial College of London, MSc degree from Mathematics from University of Cambridge, and the PhD degree in automatic physics from ETH Zurich. So, Angela, now floor is yours. So please, yeah, we are very much excited to hear from you. So please go ahead and.
Good. Thank you, Madhav. Good. So the topic is wind turbines and PHM of wind turbines, as you can see there. And I'll present an overview of general challenges and opportunities, I think, in the maintenance, operational maintenance of wind farms, and then more kind of an overview of different approaches of how to do condition monitoring and fault diagnostics using the data that comes from the wind farms. Right, there's a lot of data coming from the machines, and it's quite exciting opportunities there. Good. So was the introduction. So like a little bit of motivation, because I mean, probably not everyone, and maybe no one here is working in wind energy, right? So actually, it's quite a recent topic, as I'm sure you have noticed. Particularly this year, right? What you can see on this map is the North Sea, obviously, and then different stages of kind of in the planning process and construction and operation process of wind farms. So all of the colored areas here are basically wind power production areas at different planning stages. So in gray, you can see development zones, and in green, you can see these little bits of green here is what is fully commissioned and in operation. And all the other colors are basically what is on the roadmap, right? Not for this year and not necessarily for next year. This is like taking a long time, but it's coming, and it's going to power a lot of Europe's energy in the future. Good. And then this is a larger view, also showing a bit more of the Baltic Sea, which is relevant to you in Sweden, especially. You can see that there's a lot of early planning there, especially because the Baltic Sea is quite shallow and there's a lot of potential for wind energy there. Good. And then one exciting thing, now there's also talk about what is called energy islands. So like a physical island, namely here the island of Bornholm in Denmark. And then actually the Danish government plans the construction of an artificial island in the North Sea, in the Dogger Bank, somewhere here, which is going to serve as energy hubs for kind of gigawatt size wind energy plants. So that's quite exciting, I think. Okay, so wind power installations, this is an old map, just giving you an overview kind of where we are and how this is growing and what the needs are there in operation and maintenance. So this is data that was before this year, before the war, basically, and before also the change in government in Germany, which is quite important, especially in Germany for wind energy. So you can see that this is the new installations in Europe. There's not really a big trend, so it's quite so far not really taking off yet. And then this is what is projected. What was projected last year. There is a bit of increase, but not so much in gigawatts, right? Then you can also see the different kind of the main countries, like who's most important countries, basically. You can see Germany takes quite a leading role there, but also UK, all the countries basically who are close to the North Sea and the Baltic Sea mostly. Yeah, and then you can see that there's this talk. I mean, that I'm sure you noticed that the European Commission, and I think in May, like mentioned, kind of came up with a new strategy to really foster wind energy. And I think we're going to see. I'm sure we're going to see that in the next couple of years. That there's going to be more construction and commissioning. Okay, so let's come to more to wind farm operation and maintenance, and also more to the kind of opportunities that we have of monitoring the turbines, right? What's going on in the turbines. So what you can see here is, I think, a nice sketch for those of you who never thought of how wind turbines work. Maybe like obviously there's the rotor, right? And then the rotor is driven by the wind, and then it turns. There's a drivetrain here, and the drivetrain is then kind of the motion is then in most turbines, many turbines, not all, have a gearbox basically. So the rotation is then kind of the rotation speed is changed, is upgraded, and then it enters a generator. And in the generator, basically, we generate electricity, and that's what we then use. That's kind of like the short story. And we have, this is I mean, these machines, they sit in very remote areas, offshore, but also onshore, and they are designed to operate on their own, of course, without an operator nearby, and they are also designed to be monitored remotely. So modern wind turbines come with several hundreds of sensors equipped all over the turbine, basically monitoring different aspects. And you get from the modern turbines, you get like gigabytes of data per day if you want. And what kind of things are we monitoring? Well, it's all the different state variables, like for instance temperatures. You want to know what is the temperature of different components, what are temperature of starter windings, for instance, in the generator, right? In order to know whether this is a normal temperature or maybe we have discharges going on. You want to monitor mechanical properties, like for instance, accelerometers are put to monitor the vibration responses of different components to see whether you see the normal frequencies that you would expect to see. We measure pressure. We measure the properties of oil that's in the gearbox. Like you can monitor the color, for instance, to see, or the particle content to see whether there's excessive friction going on. You monitor the rotational speed, of course. You monitor the position. You monitor the position of the blades, position of the nacelle. You also monitor the environmental conditions, very importantly. What is the wind speed? What's the wind direction? What is the air temperature, air pressure? And these kind of things is kind of what we would typically get from a modern wind turbine. Okay, so wind turbines, this is a power plant essentially, and this is nothing that you just build like that and that operates for 2 years, but it's a long process, as we saw on the map, especially this planning stage, all of the feasibility studies and planning that takes quite some time. I mean, it's a commitment that is made, right? It costs a lot of money, and then there's the construction, and then from construction to basically to decommissioning. Like the lifetime of a turbine is around 25 years. And that's the time that we are interested in, that we want to monitor, and that I'm going to focus on in the presentation. Okay, so this is an overview of the cost, the life cycle cost that you need to calculate if you want to build a wind farm. And you have different sorts of costs, right? You need to pay the people who develop and manage the project. You need to pay the machines. But then once everything is built and sits there, you also need to look into and maintain, and you need to do repairs and so on. And actually, this operation and maintenance cost can make up to like 1/3 of the whole life cycle cost, especially offshore wind turbines can be quite costly because, as you can imagine, I mean, they operate in very rough conditions in the open sea, and it costs a lot of money to be able to to do maintenance work there. So so the idea would be that, I mean, this cost of operation and maintenance, if we can reduce them, that would be nice, because then we can have electricity even less expensive, right? So the levelized cost of energy is going to be reduced then. So that's one of the motivations why we look into PHM of wind farms. Okay, so this is an overview of the different studies. This is one of them of where people looked into the known issues from different wind farms and different vendors. And so you can see that on the left-hand side, you see kind of the annual failure rate. So how often does a certain subsystem, basically, do we see a failure in a certain subsystem? And then on the right-hand side, you see the associated downtime per failure, right? So we can see that we have relatively high failure rates, for instance, in the electrical system. But then when it comes to downtimes, which is probably more interesting to operators because that's what reduces the electricity that the power that they generate, and accordingly directly affects their revenue and their return on investment. So these downtimes per failure, they are quite relevant for them. And you can see that they are drivetrain and gearbox and generator, like the drivetrain components, they are particularly can lead to particularly long downtimes because they are difficult to replace them. Good. So, well, this is just an overview of different maintenance strategies, which probably in this seminar I don't need to explain so much in detail, right? We know that there are different kind of perspectives or strategies when it comes to maintenance, not just in wind farms. So there's the idea of scheduled maintenance. This is what we find in my experience, having worked in industry for some years, this is what we still find in many, or if not most industries actually, right? You have scheduled maintenance, for instance, you buy some sort of equipment, and then you also have a service contract, and someone comes by, checks in every 2 years or 1 year with you, and then you have regular costs which you can plan, and you don't look into the actual condition of your engine. That's kind of like scheduled maintenance. And then we have what's actually happening also in industry is condition-based maintenance, right? That's what we look into here in the wind turbines, right? We want to know 24/7 how's our engine doing, how's our system doing, what does it do? Do we need to I don't know, do we need to refill the oil? Do we need to go and perform any inspection, for instance? So that's kind of like the idea of condition-based maintenance, 24/7 monitoring. And I'll introduce or give you an overview of some machine learning approaches that we can use to kind of automate this a bit more. And then there's this holy grail idea of predictive maintenance, which, I mean, in my professional experience, having worked in industry for some time, it's not present in industry so often yet. So the idea would then be that we do condition-based maintenance, but then on top of that, we are able to estimate how long does a certain subsystem or the whole system live or until maintenance is needed, right? This is something that we see maybe more and more in batteries, for instance, but not so much yet in wind turbines, for instance, in industry. Okay, good. So so let's look a bit more into the different systems. I spoke briefly about this already. So we have different subsystems, basically. So there's the rotor, right? And there's the blades, and the blades, they are pitching. So they are kind of, the position of the blades is controlled towards the wind in order to regulate the speed of the turbine. So we have a pitch system and an associated monitoring of the blades and of the pitch system. Then we have the drivetrain. So we want to monitor the vibrations. This is like accelerometers are quite important for the gearbox, but we also want to monitor, for instance, oil properties in gearbox oil. And then there's the electrical system here in the generator, and there we look into, for instance, temperature monitoring, and discharge monitoring is also quite important there. It depends also on the type of whether you have a wind turbine with or without a gearbox, so that there are different types of generators, and then associated different types of monitoring come with it. Okay, and then on top of that, or in addition to that, we also have the data from the control systems, SCADA data. Like SCADA is supervisory control and data acquisition system. That's and that data has also been proposed and is actually quite popular nowadays for monitoring the condition of wind turbines, especially because you don't. It more or less comes, if you are an operator of a wind turbine, this SCADA data comes to you more or less for free. You don't need any additional sensing systems. You don't need to install additional vibration monitoring systems and so on. That's why SCADA monitoring has become quite popular with operators and also in research. Yeah, so here's another list of what we have available. Like I mentioned, we have monitoring all different aspects. We even can also monitor, for instance, the motion of the tower to to infer something about the structural integrity of the tower. So there's also vibration monitoring systems for towers, for instance, which is not listed. Yes, I have listed it here as well. Good, and so in this presentation, I'm going to give some examples of vibration monitoring, like I will introduce how we propose to use convolutional autoencoders as a sort of to kind of monitor the normal behavior and then detect deviations based on vibration responses from components. Like I'm going to go into this in a couple of slides, and then also give you an overview of SCADA-based monitoring. Good. Okay, here's another overview of the different components: the rotor, the main bearing, main shaft, and you have like sensors all along the drivetrain basically. Then you have the gearbox bearing, which is also like a component where you often have that's a sensitive, like an important component to monitor. You have the gearbox itself, and then the generator shaft and the generator. Good. So vibration monitoring of the drivetrain, yeah, is one topic, but I'll go into this in more detail. So I'll jump over the slide, coming to this in a few minutes. Yeah, and then SCADA-based monitoring, how does that work? Well, as I said, the SCADA data come from the control system of the turbine, right? So the turbine is automatically controlled, and that system requires data about the angles, for instance, of the blades and the temperature of different components. So you have this data more or less, like you have it available anyways. You can make use of it. It comes at regular intervals every 10 minutes, and that's kind of like it's quite convenient also to use if you want to do normal behavior modeling of wind turbines. Okay, so what does that look like, to give you an idea of this data? So SCADA data, which I'm going to speak about now. SCADA data is basically like comes every 10. You have 10-minute data, and these would be average values, and you often also get like a little bit of statistics around this, mean and then maximum, minimum, some standard deviation. So over 10 minutes. And then you have this, you get this data like time series of several hundreds, if you want, probably even thousands of variables, depends on the manufacturer. So typical variables that you look into are, of course, the power. That's the output of the turbine, the active power generation. In here, this is shown in kilowatts, and this is time in time steps. In one time step is correspond to 10 minutes, so this would be something like a week, I think, on the x-axis. And then you have the wind direction here as another example of one of the several hundreds of variables that you get from the SCADA system, and the wind speed, right? And just, I mean, for those of you who have never looked into such data before, you can already see the direct relation between the wind speed here and the power, right? So you can see that once the wind speed goes up, we have more power, and then it goes down, we have less power. So there's like a third order polynomial relation between the power and the wind speed, which is quite obvious already from these plots. And then other variables that are of interest are, for instance, the rotor speed, the generator speed. Those two are linked, of course, and then the current that is generated. Just an example of what this data looks like. What you can see immediately is also how kind of fluctuating this is, right? This is not a nuclear power plant where you always have the same amount of power and things go smoothly and slowly, but this is quite stochastic, depending on the wind and the meteorological conditions. Okay, so now let's. This is supposed to give you like a little bit of an overview of how we can use this to construct machine learning models. This is what the presentation is about, right? So we have. It's basically regression models, right? You have input variables that need to be defined by you. Usually, this would be variables that kind of drive the whole process. In particular, the wind speed is a good candidate there. If you want, for instance, to model the power production of the turbine, but it depends on basically what you want to look into, right? So very like variables that we also are quite popular for normal condition monitoring. Popular target variables would be also the temperatures, right? We want to monitor temperatures of different components, the components that I've shown you, like the gearbox bearing, for instance, and all the different components where we really want to know what is the current temperature and is that in the range that we would expect it to be depending on the current and the past wind speeds, right? So that's why we also like do normal behavior models, like regression models of temperature variables, right? And so here on the right hand side is typically like three very simple examples of what this would look like. For instance, I mean the most simple examples are actually quite. This is called power curve. Like these type of models have their own name because they're so important in wind farms. They are called power curves. So this would be the active power as the target variable, and the input variable would be the wind speed, right? This is very important for operators because that directly determines, they want to know exactly what this curve looks like with high accuracy because this is their revenue, right? So when they want to they want to know how much power will I get tomorrow, and so they look at the weather forecast that gives them the wind, and then they can convert this into power. Which depends, this relation depends, of course, on the turbine model that you have, but also on the site, for instance, right? Because surface roughness, like the wind conditions might be different. You might have wake effects, like wind shadow effects from other turbines. And so this power curve is usually estimated from past data of that same turbine that you look at, right? It is from historical data. So you have turbine-specific models. We usually have turbine-specific normal behavior models. So these models are called normal behavior models, and we can have this is a normal behavior model of the active power generation. But at the same time, if we are not interested in monitoring the power, but if we are more into health monitoring of different components, we would, for instance, come up with a normal behavior model, for instance, of the temperature of the generator bearing or something like that, right? And then we would need to put some thought into what input variables would we have here, which are the predictors, basically. Okay, so and then this plot here is to show you how strongly correlated some of these or many of these variables are actually, right? So you can see here the wind speed, and then this is the power, and the black curve is basically in 3D, and then the grayish curves are projection. The grayish curve here would be the power curve. So power is a function of wind speed, and then the dark gray curve is wind speed versus the rotor speed, right? And then, as I said, there are hundreds of these variables, right? This is only 3 of them. So you can imagine that there's a huge vector space behind this, which kind of gives you what the normal operation that defines you the normal, like depending on the input variables, in particular wind speed, you get an idea by learning these models where you should be in this large vector space if the turbine is operating normally. Okay, so but by the way, in case there are any questions, please interrupt me. I hope if it's not, I have no idea whether this is like too boring or too fast or whatever for you. Right? So just interrupt me in case there's a question. Good. So this slide is just meant to show you what I find personally exciting and nice is that this is not just, I mean, these are not just nice papers, but they are also, this is also applied in a product. This is actually applied. There are this is, for instance, the company I work with is a Swiss asset management company of managing a large portfolio of wind farms and solar farms, and such companies use such models. Also, large utility companies, energy companies work with these kind of models. And here, what you can see in this example is actually this a wind farm, commercially operated wind farm. I am not allowed to tell you which one. It's an onshore wind farm in Europe, and you can see from that we have plotted something like almost 2 years of data here. And in red, like using this normal behavior modeling, as I have just explained to you, like these basically machine learning regression models. These are, I mean, you can these relations here, you can use any sort of favorite algorithm that you like here, regression algorithm, be it a neural network or a random forest or whatever you prefer here to fit this kind of a model, right? And if once you have it, you can have it operate, like you can use it in operation, and then you can basically detect when things are not as they should be, right? When you have your, like, using this model, you know where you should be in your vector space, and if you're quite far away from that location, then you know, or you get an idea that probably something is not as it should be. And it's kind of, it's an anomaly detection approach, basically, because we, as in many industries, we don't have labels, or very rarely we have labels. So this is mostly kind of unsupervised approaches. And this is an example where this is in a product and it's like in a software that you can subscribe to as a service, and that is in operation, and where this has been basically, these models have been effective in detecting maintenance needs, basically. So here, these are two examples of where gearbox temperature and the gear oil, like an oil temperature, was monitored and were found to be not in the normal range, basically. Like, this is not a, this is not a, like, the norm, to define the normal range here is not trivial, because it very strongly depends on the current and past operating conditions, right? So it's not just constant and then you define a range, but we have to really know the previous, the current and the past operation. Good. So let's go a bit more into challenges and opportunities. Now, I hope I gave you like a short introduction into what I know is, I mean, what from my experience is the most popular in practice approach to data-driven condition monitoring and fault detection. But now let's take a bit of a wider view on the question of what are challenges and opportunities in prognostic and health management of wind farms. So if we go like, if we don't just think about the machine learning models, but also about the practical maintenance, then we will very quickly see that there are quite substantial challenges. If you look in these at this plot here, for instance, that shows you the European offshore wind farms a couple of years ago, like in construction and plant. The blue ones were operating already, and the yellow ones were kind of in construction or in planning stage. And what you can see quite clearly, this is water depth in the North Sea and Baltic Sea. And this here is the distance to the shore. And what's quite obvious is that the kind of best locations, I mean, like subtracting all the locations that are out of question because of environmental and other, like ship routes and so on. Like, if you just look at the locations that are possible, basically, then the kind of best ones, the most suitable ones, because of course, they were taken first, right? The ones that are in shallower waters and that are closer to the sea, and that's what is quite visible here. Lots of wind farms are kind of not so far away from the shore and at lower, at shallower water depths. And now the newer, like the future farms, they go in the other positions. That means they are further and further away from the shore. And that means, if you look on the right-hand side here, that also means that you have longer and longer travel times if you want to perform maintenance there. And that means also that for the really far away wind farms, that actually you can't just go there from a port, board a boat and just go there. And it also won't suffice anymore to go there with a helicopter. But what the operators are planning is to have fixed boats there, that like ships, which offer accommodation. You have like permanent crews that are permanently at the offshore farm. And so that's kind of like an entirely new maintenance concept that one needs to come up with. Okay, then other challenges, like data like machine learning related, but also other non-machine learning related, just in more or less random order. So for the machine learning models, the big challenge is, as in other industries also, is to generalize those models across turbine types. Another kind of challenge, or just a reality that we face, is that we have, as in most industries, that we have basically no labels, no ground truth, right? We have the SCADA data, we have the sensor data, but then how to interpret that data, we have sometimes maintenance logs, log files. Sometimes we need we have some information by speaking with the operators, but generally we have no clean, nicely labeled data sets. Then other kind of realities and then resulting challenges is that turbine sizes are increasing. They are growing quite fast. If you can look on the right-hand side here, the hub heights, for instance, they are growing. It means you need to, if you need to perform maintenance there, right, then you are at much higher altitudes there. Accessibility, I mentioned that already. Offshore turbines are much harder to access. Then we have also floating turbines. I'm not sure, maybe this is something new for you, right? The offshore turbines, they're not just offshore turbines basically on fixed steel and concrete constructions, like with fixed monopiles or tripods, but they're also floating turbines, right? So these also require their own maintenance concepts. Okay, then other challenges that we have is, cost of data acquisition, storage, and computing time. That actually becomes relevant because, as I mentioned already, we can have gigabytes of data from such turbines, especially if we look into accelerometer data, where we have kilohertz sampling rates, and we really need to decide how much and which parts of this data do we want to keep and which data do we not want to keep. Lack of sensor data for training supervised models. I mentioned this already. Then related with this whole aspect is we have few fault observations. We have a diverse range of fault types. Then we have diverse range of models, manufacturers, and so on. Sorry, there's a noise. Is there a question from someone? No? Okay, good. So maybe I try and speed up a little bit because I also want to speak a bit more about the research that we have done. So more on the opportunity side, right? I spoke a bit to give you a brief idea of what challenges there are, but then there are also, I think, quite some opportunities, apart from the fact that that this is overall a very exciting research area, but we have also new ways of acquiring data, for instance, by working with drones and autonomous systems. For instance, drones are already in place for blade inspection, and you can fly the drones around the turbine, and then you can take pictures of in visible or whatever range you want of the blades to see if there's some degradation going on. But then another, I think, opportunity is that we have different source of information, right? I mentioned the SCADA system. I mentioned different types of sensor systems. We have also very high frequency and high information vibration data. We have drone observations and kind of combining these different data sources and making information, obtaining information from these combined data sources, I think is a great opportunity. And then we can also, I think, opportunities come from the fact that we can apply different kind of new machine learning AI algorithms, for instance, transfer from the field of transfer learning, and try and extract knowledge from across fleets, for instance, not just from one wind farm or even only one turbine, but trying to learn from, for instance, all the wind turbines that are out there from one particular manufacturer and model. That would be nice. But then we also run into situations, problems like, where do we get this data from? Because unlike in other industries, it's not so easy to actually obtain this data, the SCADA data, and also the other sensor data, because on the one hand, the manufacturers, they are not at all interested in giving access to this data, and the operators say, well, they are concerned with their operational business, and yeah. Good. And then, I mean, one other big opportunity or field of source of opportunity is kind of combining physics and data-driven PHM models. There's actually quite some potential, I think, because wind turbines they can be physically modeled, unlike some other systems maybe, but there's quite detailed physics models, and those can in principle be combined and with data-driven models to to obtain more information about the health of the turbine. Good, yeah, and this is just to get you an idea, or to give you an idea of the different scales also, on which we can look, at which you can look. For instance, right, there are bearings, but we can also try and model. Are we modeling the whole gearbox, or even the whole drivetrain, a turbine, or even a wind farm? That's one of the questions that you need to decide when you want to look into such a study. Good. Now, the next couple of slides are going to look into normal behavior models more in detail, some research that we did there. And then I'm also giving a little introduction in how we use the convolutional autoencoders. So this is basically the next, for the rest of the talk, for the next 10, 15 minutes or so, I'm going to present some results that we have been doing in this field. Okay, so we looked into this already. Normal behavior models can be used for diagnostics, right? So I presented this SCADA data to you. I also explained that you can come up with what is essentially a regression model that you can fit with an algorithm of your choice, such as like a neural network. And then you have a target variable, one target variable usually, and that is the one you want to monitor. For instance, if it's the power, then you might be interested in detecting underperformance of your turbine with such a model. Okay, so how does this work generally? It's kind of like I think a relatively generic anomaly detection approach. So you have SCADA features. These would be the variables that I mentioned before, right? For instance, this could be the wind speed. This could be the rotor speed. Yeah, we have lots of different SCADA features that you could use in principle. And then you need to decide, okay, what are the monitored variables that I'm interested in? For instance, am I interested in monitoring the power? Like, I want to know what power do I expect? Or am I interested in monitoring the temperature of the generator bearing, for instance, right? These are typical target variables that are used or that are of interest in practice. Okay, so and then with these variables, you can come up with what is called the normal behavior model, right? You model the expected behavior as you have seen it in the same or other turbines, healthy turbines in the past under similar operating conditions. And then you can basically, what behavior you should see, like the expected behavior based on your model. And given the current condition, current wind speed, the current air density, air temperature, which are important also for if you want to have a power production model, for instance. And then you can compute residuals, right? You look at the difference basically, and then usually what you need is some sort of alarm criterion, right? Because this is an unsupervised approach. You need to kind of come up with a criterion that tells you when is my residual, or how long do I need to have a certain threshold exceeded to be able to say, well, this is now I should send an alarm or issue a notification to the operator. Okay, this is an overview of how we can use normal behavior models for fault diagnostics, and it's actually quite popular in practice. Here I'm showing you an example of where we use this, I think, quite successfully, and we published this also 2 years ago. So this is a model we used here, we built a model of the power, like the expected power. And what you can see quite nicely, for instance, if you look at this plot, I hope you can see the mouse. In gray is the kind of the expected energy, power integrated over time that the turbine produced. And you can see here, this is 10-minute time steps. It's again like a 1 week period here on the x-axis. So you can see that in green that the green line, the expected power production, and the blue, the actual power production, they match really closely, right? So we have quite an accurate model, normal behavior model. And then at some point you see that there's a gap, right? The expected power production is usually, I mean, it's higher than in such a situation, higher than the actual power production, right? And this gap is, of course, of large interest to the operators, because, as I said, I meant several times already, this is directly affecting their revenue, right? If you have a 10% less energy, then that means 10% less revenue for them usually. Good. Another question is, I mean, that's all we have. We have the SCADA data. What do we do with it? We have no additional information, right? We don't know what exactly happened. But what we can do is we can look in other variables, and we did this, and we found that the blade angle of this turbine had an unusual angle, and also we found the hydraulic pressure of the system that kind of actuates the blade angle. It also had showed it dropped significantly, kind of simultaneously to this underperformance in power. So from this, what can you take from this? Well, it looks like, I mean, we can't confirm this because this is all unsupervised, but it looks like one should have a look at this hydraulic pressure system that is actuating the blades, because it might be that the blade angles are not in an optimal position, and that is why we see this underperformance. That's kind of like the hypothesis that we would put from such a study to the operators and the maintenance staff on site. And here you can see also like the pitch angles, the blade angles during the event compared to what they normally look like. Okay, so normal behavior models. This is from a paper by Mike Schlechtlingen. He's in charge of operation, like data-driven condition monitoring at NBW, like one of the largest German utility companies, and they have several wind farms offshore. And this is, I think, a small and outdated idea and sketch of what is in place at NBW, at this company, in terms of normal behavior models operationally. So what you can see here is on the left-hand side, the input variables and then the output variables. And each line is basically showing you how input and output variables are linked in, I think this is like 40 or so different models that are sketched here, right? Okay, so if you want to look more into this, I put some, I just put on the slide also some references for those of you more interested. So this is one of the first, if not the first paper that suggested this SCADA-based monitoring. And this is this paper that's shown here on the right-hand side, on the left-hand side. And then here's an overview of, this is a review paper, and this is my work that I did last year. Because looking at this, what is in place with many operators is that there's lots and lots of them, hundreds and thousands of single target models, right? You always have the model like, yeah, I want to model power, and I do this with these input variables. I want to model the hydraulic pressure, and you do this with these input. I want the rotor speed, So I have lots of single target models. And so what I looked into last year was, I mean, why not have less of these models and just do like multi-target models? Wouldn't we even be able to gain from an increase in accuracy from the fact that these models could actually learn how the different target variables are kind of related to each other? And kind of that was the study that is plotted here. And I showed in this study that, at least for the example that I looked into in this study, the single target models and like the multi-target models can obtain the same accuracy as the single target models, but you reduce the number of models, which is quite nice. And in some cases, I could even show that you get a higher accuracy. And higher accuracy of such a normal behavior model is quite important, because it means that the more accurate the model is, the clearer you will see deviations. The earlier you will see deviations, like the earlier you will be able to trigger an alarm with your notification system, basically. So the more sensitive you are to unusual situations. And that means that the earlier you will be informed, and the earlier you will be able to perform maintenance or to plan maintenance. So accuracy of normal behavior models is important. Okay, so this is just showing that in the cases that we looked into, they have comparable training times. The multi-target models were not extraordinarily more expensive, basically. And then this is a study. I don't, because of the time, I don't go into this in more detail. Where a study where I showed that you can even kind of get more accurate with the multi-target models, and then you kind of can see occurring faults earlier on, basically, which is quite relevant in practice. Good, let's go to the next one. So this is vibration monitoring, which I mentioned already, a study that we did just recently with 2 data sets, one from an operational commercial wind farm, and one from the NREL, that's the National Renewable Energy Laboratory, like a applied research organization in the US. So one was from a commercial wind farm, and the other one was from test bench measurements of 2 quite large wind turbines. Okay, so this is a cross-section of, or a sketch of a wind turbine, and you can see here the positions where the accelerometers, vibration measurement, like you measure the acceleration, and then can use that information, basically can convert this into a time frequency analysis, and then look at the spectra and how they evolve over time, and depending on the operation conditions. So these red arrows indicate the position of, or like the components that are monitored by these, in this case, 8 accelerometers from which we had data. So this is showing prior art. So how does vibration monitoring work usually, and also in wind turbines? Well, usually what you do is you look at specific frequencies, right? If you want to monitor a certain gearbox component, then you often know that there are characteristic frequencies, like the meshing frequency, the frequencies with which the gears mesh, right? And then you monitor those frequencies as a function of how fast basically the rotor rotates. And then you just watch the frequency and the amplitude. That's kind of like a typical situation. So, and then there are more elaborate like things, but what you always do, or what you always did so far, is that you define the features that you look at beforehand, right? So you need quite some knowledge about like what ratios of amplitudes do I look like, what is kind of like the envelope, like you need to know, need to have kind of invested quite some time there in order to define the features that you want to monitor once the turbine is in operation. And what we have proposed and demonstrated in this case study is that we actually don't want to define these features up front, but we want to monitor the spectra and then kind of look for when the spectra change and do that in an automated manner. So here you can see from these 8 sensors that I just showed you, these red arrows, you can see measurements, this is a frequency measurements up to 1000 Hertz, which is where most of like the first several hundred Hertz is where most of the action and interesting information is in a wind turbine, because that's kind of like that's where lots of the frequencies are, characteristic frequencies are situated. So here we compared 2 wind turbines, WT1 and WT2. These are always the 2 wind turbines, and we compare the spectra, like part of the spectrum, the first 1000 Hertz. We compare them for these 2 sensors. So the 2 wind turbines are identical in construction, same exact model, same exact setup, design, everything. But one has, the only thing we knew was that one has kind of a fault in one of the monitored components, and the other one did not, right? So, and yeah, so I hope you get the idea. So this is the first wind turbine, sensor 1, second wind turbine, sensor 1, and you can just visually already compare the spectra, right? And now you can do this also for the second sensor and for the third sensor and so on, right? And then you do this over time, and at some point, maybe you notice, okay, so one of the spectra changes, right? So what did we do to automate this? Well, we took the vibration measurements, we constructed, I see I need to come to an end. Let me try and wrap up in a couple of minutes. So from the vibration measurements, you construct spectrograms, and then these spectrograms, well, you can just treat them as images. You put them into a convolutional autoencoder, which is kind of like shrinking, compressing. Basically, it's like a compression algorithm. It compresses and maintains only the most kind of relevant information. Then it will trained to reconstruct the image, right? And so we have here the reconstructed spectrograms, and then we basically compare the actual spectrograms with the reconstructed ones, and the difference is quite similar to what I've shown you before. This residual basically is then like this, yeah, when we are not able to reconstruct the spectrogram nicely, then it is an indicator of that something has changed basically in the spectrum. Okay, so what does this look like? This is the original, one example of an original spectrogram, and then here's the reconstruction with the convolutional autoencoder, and this is with another, like a dense autoencoder. And let me just jump to the results and then kind of wrap up, because we're quite close to the end already. So what we found is that this approach works actually quite nicely. We for these two sensors, sensor 7 and 8, from the sketch that I showed you before of the drivetrain, right? We see that the reconstruction error is larger than, well, kind of above the threshold here, or it's quite unusually large. Again, this is an unsupervised approach, so we can only say, okay, this is an unusually large reconstruction error. And we can also kind of illustrate what this looks like over time. So this is the reconstruction loss over time, and we can see that there are episodes here where it's much larger than for the other sensors. By the way, I should say that it's important to always take these spectral measurements at the same rotor speed, basically. So this is kind of triggered. So all these measurements were taken at the same rotor speed. Otherwise, you would, yeah, that's kind of to make sure that you always measure under the same conditions. Good. And then maybe the last thing to mention here is we also compared this with another approach where we used isolation forest. So basically, we only used the first part of the autoencoder to kind of compress these images, and then we used an isolation forest, like an outlier detection approach, and then constructed anomaly scores, and using then, this is a visualization histogram of these scores. And you can see that is relatively consistent. So again, the sensors 7 and 8, they stand out. Okay, good. So I'll jump over the summary and just maybe briefly touch on this last aspect that we're currently working on, and also already submitted some work on. So we're also exploring currently the potential of transfer learning approaches. So for instance, to enable an earlier detection of operation faults. So the idea is that you have access to nice data sets from several wind turbines, and then maybe you also have some other wind turbines where you have not so nice data, you have less data, or you have few observations of faults, and in one way or the other, you have kind of scarce data for these other turbines. And then the idea is to try and use this knowledge that we have gained, that we've learned from these, what we call source wind turbines, and then to transfer this and kind of enrich the data, the scarce data that we have in the target wind turbines. So this is a current research project, and we see quite nice results. So this is just showing you, we're comparing different transfer learning strategies, and see that some of them actually are more beneficial than others and can lead to earlier detection of faults. Good. Last not least, if you give me 20 seconds more, we have some vacancies in my group at Bern University of Applied Sciences for postdoc positions. So in case you're interested, so there are 2 of them in this project that I just mentioned. So in case you're interested, then please visit our website or get in touch with me directly. Thank you so much.